thank you again to the organizers for this very nice workshop. So I am going to talk about assembly bias in the cosmic web. So we're again talking about dark matter halos. And this is going, so mainly I will talk about a recent paper with collaborators at IAPE here in Paris, and also some earlier works of mine. But before going into that, I wanted to do some propaganda about ICTP-EAIFR, which is the institute I belong to. So ICTP-EAIFR, EAIFR stands for, so maybe I think people know ICTP, but EAIFR stands for East African Institute for Fundamental Research. So it's ICTP Partner Institute, one of the two partner institutes, the other being in Sao Paulo in Brazil. And this one is in Kigali, in Rwanda, so within the University of Rwanda. So it's very new, has just been established. It aims at becoming a science hub for Africa, and it wants to replicate the model of ICTP. I don't know if you're familiar with it. So there are students, so there's going to be master students and PhD students, a core of resident scientists, a strong visiting program, so you're all welcome to visit over there, and scientific activities. So all this in close collaboration with ICTP in Trieste, so hopefully maybe one of the next cosmology schools will be held over there instead of on the seaside in Italy. So for those of you who don't know where Rwanda is, well, it is there, not far from Lake Victoria, so East Africa. And why Rwanda? Well, because most of you may have heard about Rwanda for different reasons than science. So there was the theater of a terrible civil war and a genocide in the 90s. So after that, hopefully the country has learned that education is a key for economic prosperity and for, in particular, scientific education. So they're investing a lot in science. And that's their, the key for, so that things that bad things that have happened in the past are not going to happen ever again. So this is what it looks like. This is called the country of 1,000 hills. So it's a landscape filled of green hills and lakes. It's very beautiful. There is also a network of modern infrastructure that is being built. This is what you see here is the new convention center in Kigali. There are still some very interesting and natural attractions like the mountain gorillas and delicious tropical fruits that you're all welcome to come and taste. So, okay, now let's come to business now. So my talk will be in two parts. The first part will be properly about assembly bias, and in particular, I will describe a completely analytical model, toy model that has assembly bias built in based on excursion sets with conditional probabilities. And in the second part, which I'll see if I actually get to, I will try to describe some work in progress that I am doing on the statistics of extrema for large-scale structure. But bear in mind that I really much believe that what people are doing in large-scale structure, so this is just a mathematical tool, but it has a lot of potential applications outside. One of is primordial black holes that is already being done, or stochastic inflation. So I think there are a lot of interactions that a workshop like this should explore. So what is assembly bias? Assembly bias, well, it's a bit of a vaguely defined concept, so that, broadly speaking, there's more to a halo than its mass. So and it is put like that, it is a rather obvious statement, and it would be surprising if it were not so. But when we try to go into more details, then it turns out to be surprisingly difficult to find what is the optimal way to describe this something else that characterizes dark matter halos. So most quantities that you play with turn out to have some unexpected behaviors in some regimes. So our approach is that because halos are not isolated objects, then their position in the cosmic web is an obvious candidate to take into account to describe the diversity of the galaxies, of the galaxy populations that are hosted in dark matter halos. So, and this is something that is, it would be stupid to neglect because the position is something that you can easily observe. And it starts to be observationally relevant because surveys now are looking at that. And some surveys like Vipers, Cosmos, and Gamma have actually found some hints of, for instance, of different mean colors for galaxies as a function of the distance to the filaments, for instance, so the position in the cosmic web. So for me, I'm not going to talk about galaxies. I'm going to talk about very theoretically idealizations of dark matter halos, which is what you get from excursion sets. So excursion sets in a nutshell is a model that says that dark matter halos evolve out of patches in the initial conditions that are dense enough to basically pull themselves together by the time you are looking at them. So if you are looking at objects today, then they have to be dense enough to pull themselves together by today. And what is enough usually is something that is inferred from spherical collapse. And in the most basic models is just the infamous or famous the critical density of 1.686. But crucially, it's not enough to be dense enough, but you also need to be the largest region that is dense enough. Because if you have a region that is dense enough that is contained in another larger region that is also critically dense, then you need to call the halo the larger region and not the smaller, because everything will become part of a larger object. So what you're doing in practice is that you take the initial density field, so the linear field, you smooth it, so you convolve it with a top hat filter, and you're asking the question whether this mean density is larger than some critical value, delta C. So again, you have delta. You convolve it with a top hat filter. So in Fourier space, this is a thing that has a lot of wiggles. And you're asking whether this is larger than delta C. It's not the end of the story, because so this is true if you are looking at halos today. If you want to look for halos that are identified at an earlier redshift, so you can divide this number by the growth rate of density of matter density perturbations. So this number is 1 when z equal to 0, but when z is larger, so in the past, this number is smaller than 1, so the threshold is larger. And that makes sense, because for an object to form earlier, it has to be denser at the beginning, to begin with, in the initial conditions. Okay, so what you're doing by implementing this inequality here is that you are actually drawing random walks of the mean density field as a function of the smoothing scale. And you're asking for which smoothing scale your density reaches a threshold. So for those of you who listen to the, I hope all of you, to Sebastian's talk yesterday, these random walks that I am dealing with, these are solutions of Langevin equation, but now with colored noise. And the noise is colored because the filter that I'm choosing here is a top hat filter. And there is no choice for that, because I'm looking at, I want to find halos. Halos are something to which either a particle either belongs to the halo or not. So it is something that has boundaries. even though we don't know them clearly, so there's no choice there's no escape from using a top hat filter. So once you if you buy that, then it makes sense to say that you can model the abundance of halos by knowing the probability of the passage of this random variable through this threshold, and these are random walks with correlated steps. So as I said, there are close analogies between this formalism and what you do with, for black holes and in stochastic inflation. So this is with a cartoon. So we are sitting at a position x, and I have a smoothing scale r. I start from a very large smoothing scale r. So I draw a very large sphere on my position. I take the mean density. For a very large sphere, the mean over density is 0, but then it changes, and it may cross the threshold at some point. When I cross the threshold, I have singled out a scale. That is the mass scale of my halo. Then my trajectory may continue and may have other crossings. But because it is only the first that I care about, then I have univocally fixed a mass scale. So if I sit at a different position, I have a different trajectory associated to a different point in space. So this trajectory may cross the threshold at a different scale. So this is a halo, is a location in the initial density field that will form a halo of a different mass. Okay. And bear in mind that because we are after the first crossing, that the first crossing can only happen upwards. So this slope has to be positive. There is no choice. And also sometimes, sometimes I will be plotting sigma. Sigma is the amplitude of the density perturbations. It is a function of r, but r is a function of mass. So the mass is just the cube of r times the background density. So all these three quantities are equivalent to each other. But just bear in mind that sigma grows in this direction, and mass grows in that direction. So large masses, small sigmas. No, there is actually, galaxies don't really destroy, so you assume that but there is an interpretation for that. I will come to that later. Yeah. Okay, so as I said, you want the abundance of halos, and in order to get the abundance of halos in this model, you need the first crossing probability of these trajectories. The problem is that the steps are correlated. So for correlated steps, there is no, which are technically called non-Markovian random walks. There is no known solution for this first passage problem. Also, if the steps are uncorrelated, there is a known solution only if the barrier is constant. But okay, for correlated steps, there is no known solution. However, the correlations, which is what brings the problem in the first place, also shows you the way out, because what the effect of correlation is that zigzags in these random walks become more unlikely, and therefore the probability of having multiple crossings of the threshold is exponentially suppressed. So this can happen, but only at very small masses. If you look at masses that are large enough, then it is enough to relax the assumption of first crossing into simply upward crossing. Remember, the first crossing has to happen upwards, and it is only the third that may happen. That's the second is downwards, so the third is upwards again. So if I only ask for upwards, I am correctly discarding the second crossing, and I may be wrongly counting the third, but this is a very small error if the steps are correlated. So having a non-Markovian problem with colored noise, in this case, it's something that helps you. So then this is the approximation to the problem. That's the distribution of upcrossing. So you need the probability that your trajectory is at the threshold, and the slope so the derivative of the trajectory with respect to sigma is positive. I'm integrating over all positive derivatives here. There is also this guy here, so there is an extra d delta by the sigma, and this is there because I have a probability of delta, but I want to end up with a probability for sigma for the scale, and therefore I need a Jacobian for the exchange of variables. So this thing is a simple expression. It's just a bivariate Gaussian. It has a simple answer. It was already there in a slightly, with a slightly different meaning in Bond et al. In 1991. And what it looks like is that this is the Press-Schechter result, the thing that people want to add a factor of 2 in order to get something normalized. But instead of adding a factor of 2, we have a more complex factor, which is also analytical. It has one parameter x. Okay, it has some expression, don't worry about it. It describes the cross-correlation between the height and the slope of your random walk. So this thing is very large at large masses. So if you plug something very large in here, you know the ERF, you get 1, so 1 plus ERF is 2, this is 1, this is exponentially suppressed, so this whole square bracket is 1. On large masses, you go back to Press-Schechter. On large masses, on small masses, you get something else. And this is actually a very good approximation. And not only it is a very good approximation, but it is also, this expression is completely generic. It's also valid for a non-Gaussian distribution. So this is also something that could be of interest for people wondering about non-Gaussianity for primordial black holes, for instance. So this is how well it works, this expression. I have plotted the upcrossing distribution against the correct first crossing distribution obtained through Monte Carlo random walks. And this is for different power spectra, for different barriers that are not necessarily constant. So it is a very generic thing. But the important thing for cosmology is this curve obtained with the lambda CDM power spectrum. And a constant barrier, so that is also well under control. This is what you would do if you were taking Press-Schechter times 2. That is what people have done for a long time. So there is a discrepancy. Okay, so this was a preliminary part to convince you that we know how to deal with the first crossing of random walks with correlated steps through arbitrary barriers. So now let's talk about assembly history. So there is more than just an information about the mass of the halo that is encoded into the excursion set trajectory. Because remember that I was saying that the barrier grows with redshift. So at high redshift, far in the past, the barrier is higher. So now imagine that, so if this is the barrier today, in the past I had a barrier which is higher, and therefore the first crossing scale of that barrier is different. So if the barrier is higher, the first crossing is at larger sigma, and therefore a smaller mass. That makes sense because in the halos are smaller in the past, and then they grow by accretion. So you can interpret this whole trajectory as giving you the full accretion history of the halo. And as the threshold drops, the crossing scale moves to the left towards higher masses. So halo, the mass is growing. And it can grow either continuously or through finite jumps. So whenever you have a dip like this in the trajectory, this is it brings a finite jump of the first crossing scale. This is something that you interpret as a merger. So that was your question, I think. Okay, so now if you look at just a very small interval around the scale, you can take a derivative, and you can take a derivative because these random walks are differentiable. They're smooth. And so the derivative tells me the local increment of the mass. So steep slope means that the mass is changing, the first crossing scale, and therefore the mass is changing, is not changing much as I move the threshold up and down. And therefore steep slope gives a small accretion rate. In fact, the slope is 1 over the accretion rate simply because I'm trying to infer the change of the x-axis by changing the y-axis. So that's why there is 1 over, so the accretion rate is 1 over the slope. Now let's let's ask what happens about if I take 2 halos that have the same mass. So 2 halos that have the same mass, they must have, in the language of excursion sets, they must have the same crossing scale. So, but then the rest of the trajectory is different. So these 2 halos that we are considering have 2 different, they are crossing the threshold with 2 different slopes. One is steeper and the other one is shallower. And the one that is steeper is, because we said accretion rate is 1 over the slope, so the one that is steeper is a halo that is accreting less today, while the one that is shallower is a halo with a larger accretion rate. The slope that is steeper also is necessarily higher at smaller scales, so I can play the game of looking at both trajectories at the scale corresponding to half of their mass. They have the same mass, so the scale is the same for the 2. At this scale, the trajectory with a steeper slope will be higher. And therefore, I can ask, what is the threshold that a higher trajectory is crossing? So I have the threshold that I look for the redshift that brings the threshold at the height that I need. And therefore, a higher trajectory will cross the threshold at a larger redshift. So this is a halo that has assembled half of its mass earlier than a halo with a shallower slope. So the time is at which a halo assembled half of its mass is sometimes called the formation time of the halo. So halos that have small accretion today also have earlier formation times. And this also is almost a tautology, because if you want to have the same mass today, but you are creating less mass today, it means that you have assembled most of your mass earlier. So all this comes built in. Now, because these walks are differentiable, a trajectory that has a steeper slope necessarily also goes to a lower density at larger scale. So this part describes the environment. So these halos with small accretion rates preferentially live in lower density environments. So this is assembly bias already. However, we want to see now what happens when you are near a structure of the cosmic web. So we are investigating a filament, and we consider a proxy of the filament as a proxy for a filament, a region in the initial field where there is infall from 2 directions and outflow from 1 direction. And we know that direction of outflow is the direction of towards the 2 nodes, while the directions of infall are where matter is flowing from the voids into the filament. So we will consider this frame, and we will move the position around where we do excursion sets to find halos around and see what happens. So more with numbers, we have we pick a large scale, which we consider to be 10 megaparsec in this example. This will be the scale of the filament. We compute the potential, mean potential in this large sphere. We take the Hessian, so the Hessian matrix, and the Hessian matrix gives you the shear on a sphere of large megaparsec. So it tells me how the geometry on a sphere of 10 megaparsec is deformed by the flows. So for this to be a proxy of a filament, it needs to be a saddle point with 1 negative eigenvalue and the 2 positive ones. The negative eigenvalue is the direction pointing towards the nodes, so the axis of the filament, and the two orthogonal directions are pointing towards the voids. So this is the Hessian matrix. I can write it as a sum of the trace plus its traceless part. And because we are dealing with Gaussian probabilities, now the effect of having a saddle point with this particular value of the shear is very simple. It's a Gaussian PDF, so all it happens is that the mean and the variance of my distribution with which I need to do excursion sets are shifted. So in particular, so the mean value for delta filtered on scale big R at finite distance little r from the saddle point is something times the density of the saddle, and this something is a correlation function that depends on r. But there is also an anisotropic term that appears because there is an anisotropic part in the, so there is a matrix, so there is the three eigenvalues with the different values introduced in anisotropy. So remember that the negative eigenvalue is the one that points towards the nodes. So in the axis of the filament, when this is in this direction, this object will be positive. This, I'm telling you, it is positive. So this will be negative. So there's a minus sign. So the whole thing is positive. And therefore, it means the mean density in the direction of the filament is higher. Not surprising again. And it is also not surprising to expect that because the mean density is higher, it will be easier to form halos. And so this is the cartoon again. Here is the direction. In the direction of the filament, you will have a higher mean density, and in direction perpendicular to it, you will have a lower mean density. So in the direction of the filament, trajectories they will be surfing a higher wave, so they will reach the threshold faster. So halos will be more massive. But at fixed mass, so if I fix the crossing scale, then I can ask what happens, what is the difference between the two positions. So a halo that forms in the direction perpendicular to the filament, so in the void, will follow a trajectory that is initially lower because the mean density is negative there. Because it is lower, but it has to reach the threshold at the same scale so that the mass is the same, then it will necessarily reach with a steeper slope, and therefore it will have a smaller accretion rate. So then we will see that I will expect to find halos with low accretion rate and earlier formation times. So this is actually what happens. So this is there are the different mass functions that as a function of the position in the frame of the saddle. Just focus on the two extremal cases. So this is a mass function at position equivalent to the filtering radius, so 10 megaparsec, the filtering radius of the large objects, and in the direction of the filament, and this is in the direction orthogonal. In the direction of the filament, it is easier to form more massive halos. In particular, I can find out what is the typical mass. It's the quantity that characterizes the mass function, or the typical sigma, because the two are related. And I can trace a chart of what is the typical sigma. Again, I see that a saddle point of the potential is also a saddle point of the typical mass of halos. So here you see the formation of the filamental work. Here you have nodes with more massive halos, while in the direction of the voids, the halos tend to be less massive. And the same for accretion rate. So this is the PDF for the accretion rate given the mass that is the same for every halo. Again, you have different PDFs for accretion rate at fixed mass as a function of the position. And you can look at what happens to the chart of the typical accretion rate of these PDFs. And again, in the nodes where the halos were more massive, these halos are also accreting faster, where the halos that form originally in the direction perpendicular to the filament, so away from the filament, these halos are stalled and are accreting less. Same for formation time, which it's basically exactly the same thing. It's hardly to see the difference, but I probably skip this and try to be faster. Here again, there is a comparison between the two charts. All I want to say is that clearly the two contours are not the same, which means that it cannot be that everything, all the additional properties are a function of some local property, like, for instance, the local mean density, because otherwise the two contours would be the same. And this is an attempt to measure these effects in simulation, a paper by Katarina Kralic, which is in preparation. And these are measurements in the horizon AGN, but without AGN feedback, not to be, just to focus on the dark matter only. And you indeed see that, at least for the large mass bin, you do have that, like, these are the white contours are the contours of the typical mass. And colors give you the contours of the star formation rate. And if you buy that star formation rate and accretion rate of dark matter are somehow related, then you see somehow the same qualitative trends. So this is encouraging. And also, when you look at large-scale bias, there are some interesting things that happen. And one question that people have wondered about for a long time is that there seems to be some inversion of the bias parameters that seem to be related with the filaments, and how the role of the accretion rate interplays with the position in the cosmic web. And indeed here we see exactly something like that. These curves are the bias parameter, so how the number of halos is tracing the density at very large scales around it, as a function of the accretion rate of the excursion set trajectories. And the different curves are various distances from the saddle point. So I see that halos that are forming near the node are tracing have bias parameters that behave in the conventional sense, so it decreases with accretion rate. Remember, accretion rate, I told you in the first slide, small accretion rate means a steep slope and therefore lower density environment, and there it is. At low accretion rate, you have lower bias. However, halos that form near the saddle point have the opposite trend, so it is an interesting thing. Now, I just want to wave my hands and say that, okay, there was a similar measurement that has been done by Tito and Lazeiras and Fabian Schmidt at MPA. So in this curve, these curves show the bias parameters as a function of accretion rate but now for halos of different masses. You may speculate that because this is the small mass, so the curve that shows the clearest inversion is the one with the smallest mass, and here you have the halos that are near to the filament, but I have told you that you form preferentially more massive halos in the nodes, where near the center of the filaments, halos are preferentially less massive, so perhaps there is something to investigate in this. And I think I have 4 minutes left, perhaps, so I will go very fast to see what I'm trying to do now. So I would like to improve over BBKS and dare to improve over BBKS by saying that the common law established by BBKS is that halos are not only critically dense regions, but also peaks in the density field. So if I look at peaks of the density field, then I know where to find the halo centers. I want to say that this is mostly right, but not completely, because actually what forms halo is not the density itself, but is the convergence of the acceleration, of the gravitational acceleration, which then forms density peaks. So I should look for convergence so for regions where the primordial flows are pointing towards each other. And the way to do this seems to look for minima of the density of binding energy. Again, not surprisingly, the energy is a dynamical quantity, so minima of the binding energy are the most tightly bound regions, so it is not surprising to think that these are the locations of future halos. So you do exactly the same thing, but you just replace the quantity. Instead of speaking of the overdensity, you talk about binding energy. Everything goes through in the same way with a bonus that is the technicality, but for the aficionados is that if you were doing the calculation that you wanted to do to begin with the density field and a top hat filter, you can't because you get divergences. If you do it with the binding energy, everything is perfectly convergent, so you can actually do the calculation without having to wave your hands and change the filter into a Gaussian or something else. So, right, and it seems to work well. So some preliminary measurements where you can actually see that this, this would like to show that indeed the Hessian of the binding energy at the position of protohalos is negative definite, as it should, or positive, okay, it has the right, is defined in the right way. I can talk a bit more about that. This is some attempts to see that actually the location of the minimum of the binding energy, which is also the location where the sphere has zero dipole. So you have been careful to put the center of your sphere on the center of mass. So that's why the inflow is maximally symmetric. So that's why you're going to form a halo, and that works better than the density peak, which is the triangle here. So this is also encouraging. And okay, this is my final slide. I say that, okay, that's not the end of the story, because actually there's a lot to be done. I've been continuously been talking for 45 minutes now about a constant threshold, but this threshold is actually not constant at all, so it's not exactly critical. There is a lot of scatter. If you find halos in simulations, you trace the particles back to the initial conditions, and you measure what the density is in a sphere of the corresponding Lagrangian radius, then you get something correct at very large masses, but a lot of scatter at smaller masses. Because there is a lot of scatter, it means that there are variables that you have not tracked correctly. And the main culprits are the shear, the ellipticity, and the velocity dispersion. There is already some work done on the shear by Porciani's group, but also Asim Paranjap and Ravi Sheth, and Emanuele Castorina and Oliver Hahn. But the final word is not said yet. And this is also important for assembly bias, because if you have a barrier that depends on the shear field, and the barrier is higher, a barrier that is, so if you know that larger shear gives you a higher threshold, then a higher threshold will select the excursion state trajectory with steeper slopes and therefore with smaller accretion rates. So this is also a source of assembly bias. But that's not the end of the story, because the shear is not enough to explain for the scatter. You also need to quantify velocity dispersion, so that's something that I'm trying to do now. And that is it, I think. So this is my summary. I have I had some fun with dispersion sets. I hope I convinced you that assembly bias comes built in with in your analytical model of structure information. There is no need to do any extra effort, and you just need to account for enough variables. So the predictions are qualitatively correct in comparison with simulations. So what we used is a proxying for filaments that are a saddle point in the potential. And that has effects. So the position in the cosmic web strongly impact the accretion of your dark matter halos. Of course, if you want to do real stuff, then there will be AGN feedback. But apparently AGN feedback is, it evens the effect, but it's not enough to erase it completely. Also, we have some preliminary results for that. And of course, if I want to be more quantitative, I need better models to explain the scatter of the threshold. So there's a lot of, because that's where the physics is. So there's a lot of room for improvement there. Thank you very much.